Okay, let's continue. We continue with the point that Carlo was describing, nodes, quantum geometry of a node. Exactly the discussion of this morning. And please keep on asking questions. Something that can help us, often I go quickly through my slides and my things that I prepared. You find them online, they are on the website. So for you it's easier to just download them and annotate them instead of copying things. They are all there, okay? There's a lot that I want to cover. Some of this is technical. I think it's necessary to have a bit of mathematical tools so that you can clarify things by yourself by working them out. I'm just going to choose things points that I think it's useful to have completely clear and build on them. And the tool, the mathematical tool that we need is intertwiners. It's a topic in group representation theory. I'm not going to present it from that perspective, but more, we have all learned quantum mechanics of one body or one spin, and then of two spins, and then of three spins. I'm going to build it out of that, okay? Then I'm going to start with something completely different. The tetrahedra, Carlo explained how the tetrahedron can be described in terms of areas. We're going to do the polyhedron, many phases. In the last part, I'm going to show you that if you quantize this, you get this. Okay? Or if you take this and you take the classical limit, you get this. So they are the same thing. Okay? And that's a surprise. Okay. So let's start with the mathematics. Or the way I'm going to present it, the physics of a many body spin system. Mike, thank you. Oh, good. Thank you. Can you hear me well? Yeah. I'm recorded. Okay. So, first point. Consider a system of n, let's say, particles or bodies. Each one of them has a spin. It could be all spin 1/2, but let's be more general. From J1 to Jn, and it's n of them. So what's the Hilbert space of the system? Well, it's a composite system. It's just the tensor product of the Hilbert spaces of each one of them. And each one of them, I'm saying it's a particle, but I'm not really interested in the position or the momentum. I'm only interested in the spin degree of freedom. Okay, so each one of them is a 2J plus 1 dimensional vector space. All this we know. The orthonormal basis is just Jm for each one of them. Okay? And so now I'm ready to say what is an SU2 intertwiner. You take the Hilbert space of this system. It has a big dimension is 2J plus 1 times 2J plus 1 plus 2J plus 1. And inside there, you look for a subspace of states that are invariant under rotations. So here, Carlo used this notation. You take the tensor product and then you take the invariant under SU2. I'm denoting it here with a 0. So I have to say, what is this 0? In what sense it's invariant? And before giving you definition, I'm going to go through examples. The first example that I think we have all seen is take 2 spin 1/2. The Hilbert space is 4-dimensional. The basis up, up, one down, the other up, one down, both down. Okay, it's 2 times 2. This is the basis that diagonalizes the spin of the first direction z and spin of the second direction z. So what is the intertwiner Hilbert space for this system? It's the set of states that are invariant under rotations. And one standard way of building it is think first of the total angular momentum. That is J1 plus J2. Instead of diagonalizing the spin of each one of the two, you can diagonalize the total angular momentum and total angular momentum on direction z. If you take total angular momentum equals 0, that's what we call the singlet. Okay? That's the intertwiner. That's the intertwiner for 2 spin 1/2. In fact, the other one, the triplet,
this one transforms as a vector. Okay? And so you had an Hilbert space that was 4-dimensional. These three, you throw them away because they transform, and this one you keep. There is a unique intertwiner between two representations of SU2. For 1/2 is this one. Okay? Yes?
Is this triplet also for J1 plus J2?
You mean?
I mean, you had on the right side of the slide J total equals J1 plus J2, two angular momentum. And is the triplet also applicable for this case? Or did I...
4-dimensional Hilbert space, you can use this basis, or you can use the basis singlet, triplet up, triplet 0, triplet down. Okay? And now we are projecting away everything that changes. So this one changes because this one points in a direction.
Okay.
So this is intertwined. It's the part that is rotational invariant of the Hilbert space. Okay? Let's go ahead. I'm going to do one more example, or maybe two. Better two. Okay, so I did 1/2, 1/2. Now I'm going to do 3 objects. I'm going to do spin 1, spin 1, spin 1. Okay? So spin is 1, 2j plus 1 means 3, so this would be a Hilbert space that is 3 times 3 times 3-dimensional. Okay? How many intertwiners, how many objects there are that are invariant under rotations? It's going to turn out again that there's only one. So let's find it. When you study composition of angular momentum, there's something one learns that is, if I have to do 1 times 1, you find 0 plus 1 plus 2. I guess this is familiar. And then there's still a times 1, so I do it. And I get 0 plus 1 plus 2 plus 3 with some degeneracies. I'm interested in this 0. So how can you think of that 0? One way of thinking about it is you have two particles spin 1. They interact, and you ask what's the probability of getting one as a Clebsch-Gordon coefficient. But there's a way that is easier to think about it. That is, can you think of a tensor with 3 indices, each one of the indices that transforms as a vector spin 1, it is invariant under rotations. Is there something that you can write that is invariant under rotations that has these properties? Any guess?
Maybe something contracted, someone with the epsilon tensor?
Okay, and I need indices that are...
Yeah, but if they are vectors, they have like vector indices, so you can contract them.
Good. More suggestions?
Maybe like if it's totally antisymmetric.
Totally antisymmetric. So, let's see. So, you can think of one of them as a vector, I, x, y, z. And the question I was asking is, can you come up with a tensor with 3 indices I, j, k that is invariant under rotations of all 3 of them at once? Well, epsilon I, j, k does the job, right? Levicivita. Okay? So often when we say intertwiners, we think of a node with legs. Each leg transforms under a representation. And this is also a way of speaking about a tensor, sometimes written I M1, or maybe tensor T M1, M2, M3, and so on. And so what I'm asking is, can you write a tensor that transforms in the correct way? And also, how many of them there are? I want really a Hilbert space of these tensors. And so, yeah, I'm saying there's just one, epsilon ijk. Still have to convince you that there's just one. This is an example. Okay? Let's do another example. Can you think of something that has the right properties and it's of the form, so I did this. So it was 1, 1, 1, I, jk, and I'm saying this is equal or proportional, I should say. Let's write equal, epsilon jk. Now I want one that does 1, so I, and then let's say 1/2, 1/2. So yeah, I should put alpha and beta so that this is a plus or minus 1/2, plus or minus 1/2. Any guess what is a tensor with these indices that transforms in such a way that if I transform each one of the indices under a rotation, it remains the same? So that it's, yes?
Epsilon ijk, sigma I, sigma j.
Let me see if I get it. So you're saying I do epsilon jk, that is the same one. And then what do I put?
Times the Pauling matrices.
And how do I contract them?
Ijk is what I was guessing. Sigma j, sigma k.
So you're saying I put 3 sigmas. Or how many sigmas?
2. Sigma j and then sigma k. Sigma sub j, sigma sub k.
But okay, sigma sub j, sigma sub k, but sigma has alpha alpha prime, beta beta prime. So I get one index I, good. Then I get 2 indices. So this looks like it has too many indices. So almost, but I need something just with 3 indices. We are close. Any guess?
Look at the black one.
Sigma itself.
Sigma itself. Good. Sigma itself. So if you ask what is this thing, it's not bad. This is just you start with this, and then you keep branching one more. And so what you gave me was something with a bit more legs. Sorry, one and 1/2. It's 1 leg 1 and 4 legs 1/2. Okay, so here is the 1, 1/2, 1/2, the sigma. Okay? Now we need a machinery. We cannot keep guessing, right? So there's a topic in quantum mechanics that there's no doubt you all looked at. When you do combination of angular momentum or coupling of angular momentum, you study the Clebsch-Gordan coefficients. It helps a lot to look at all of that mathematics and think about it again in terms of diagrams. They are just dots with legs. You have 1 that goes into 2. And say this is Jm, J1 M1, J2 M2. These are Clebsch-Gordan coefficients between these two and this one. You see I put arrows. And we don't want 1 that enters and 2 that exit. Let's make it more democratic. I can flip one of the arrows. And now I have the invariant tensors that we're interested in. Okay? So that's my next page. So you often learn them in this way. No? Clebsch-Gordan coefficients. I'm saying flip this one on this other side. If you want by time reversal. And so you have something you can think of as you have 3 objects of given spin. What's the probability amplitude of finding something of 0 spin? Okay? And this thing is called the Wigner 3J symbol. You find it tabulated. You find it coded, for instance, I don't know, in Mathematica. It has the property that if these 3 m's don't sum to 0, it's 0. It has the property that if these spins are too small and one huge, it is 0. They're called triangular inequalities. Usually it tells you there's something to do with geometry. No, it's like triangles. And then there's something that is, at the beginning I was saying, I want n of them. I did 2, I did 3, how do I do n? And with 3, this is the only one that there is. With n, how many there are? It turns out that you can really use these ones as building blocks. You can build everything else out of them. It's a useful technique. You don't have to use it. It's a basis. You don't have to choose this basis, but it's good to start with it. Yes?
I want to go back a little.
Mm-hmm.
Because I see that 1 comes in and 2 ones come out. Shouldn't there be some kind of conservation of angular momentum at the vertex?
Mm-hmm. That's conservation of angular momentum. 1 times 1, you can do 0, 1, and 2. And so it can combine into 1 so that...
right.
Okay?
Yes.
So if it was not possible, there would be no epsilon. The fact that we know that epsilon exists means that this can be invariant.
Okay.
Okay? Okay.
The 115.
115 doesn't exist. 110 is good. Okay, so let's do 1 with 4. So I want something invariant with 4 legs. And I assign the 4 legs. So one way to think about it is, you think first of the first 2 legs, you combine them into something of spin k, and then you make it decay into all the 4 legs. By construction, this is invariant here, invariant here. Now we have a label in between. Okay? And just by illustrating it this way, you see that now this is not unique, the invariant with 4 legs. There are many that depend on this extra label, on this virtual spin. Okay? And just be careful with arrows. The way I described it, it was like it's a Feynman process, it's a Feynman diagram. I'm going from this way to that way. We just want all the arrows go in. Okay? Let me turn this diagram into a formula. I'm saying this tensor, this is a state in my Hilbert space, because don't forget, I'm speaking about state of n spins. So these are just the coefficients on the expansion on the Jm basis. Okay? So this one, this trivalent vertex, we learned that we can write it as a 3J symbol. This one is a 3J symbol, and then I have to contract it with a leg. And you see that there's this delta m on this side, minus m on the other side, m prime m second, because the sum of the m's has to be 0 so that it's invariant. Okay? Now, can I characterize it in a way that is a bit more physics concrete? Like, I'm really speaking about the Hilbert space of 4 spins, and I'm building a basis that is invariant under rotations. So when you build a basis, you can always think of it more operationally by saying, tell me what you are measuring and what basis of eigenstates of what you are measuring this is. And so, yeah, you have 4 spins. You can say, suppose that you measure the spin of the first 2 squared. Okay, this is an observable, and if I can find a complete set of compatible observables and diagonalize them simultaneously, I get a basis. So this is a basis of this observable, which is sufficient. There's just one. It diagonalizes it, and you can check that this thing that I was calling virtual spin is actually the thing that labels the eigenvalue of this operator. Okay. Tell me if it's too fast. If there are comments, yes, go ahead.
I just, maybe I'm jumping ahead, but what's the relationship between the valency of spins, or the number of J's, and the dimension of the system?
Good. Yeah, it scales up very quickly. So let's do just spin 1/2, okay? If you have many spin 1/2, each one is 2-dimensional. If you have n of them, 2 to the n. Now I'm looking at the subspace that is invariant under rotations. So this is throwing away lots of things. So I understand that what you ask is, how many am I throwing away? So let's do that, because it's useful to see how much we're throwing away and how much we're keeping. So we do n equal 4. So we are saying dimension of the Hilbert space is 2 to the 4. The question is, what is the dimension of the Hilbert space invariant under rotations? I'm putting this 0 here. 0 just means total spin equals 0. And so there is a way to compute it, but let's do it by enumeration. You have 2 spin 1/2 that combine. What can they combine into? This is 1/2, 1/2. They can combine either into 0, no, or into 1. And then can come back 1/2, 1/2. And so you get here just 2. Okay, so you threw away a lot of them. Now, let's do now n. This is dimension of the Hilbert space is just 2 to the n, so exponentially large. If you ask how much smaller is this one, well, you're just imposing invariant under rotations. So you're not killing that many. This is just one global constraint. So it's still going to go exponentially, just bit slower. Still 2 to the n, but there's a factor in front here. Something like n to the 3/2. Okay? That's great. Yes? Right.
Can I go? Okay, so on the blackboard you wrote 2 incoming and 2 outcoming.
Mm-hmm.
On the slide, I see there are 2 incoming on the left and 2 incoming on the right.
Mm-hmm.
So it's a little different situation.
Yeah. This is just time reversal. So it's not going to change the dimension of the Hilbert space. And that sometimes it's easier to think about it in this way, sometimes. But when I think about intertwiners, I always use the convention that I have either all of them incoming or all of them outgoing.
Okay.
Okay?
In that case where all of them are incoming, it means they have to cancel out to have the...
Also, yeah, they all have to cancel out.
Okay.
Okay?
Okay.
Let me say it in another way. This is just like, are you raising or lowering the indices? No?
Okay.
Okay? Yes?
Just to check, the delta there is m prime and should be
M
double
second.
prime?
Yes. Let me correct it. Thank you. Good. Okay. And all of these coefficients, check them. It's clear the story. I'm looking for eigenstates of this observable. Okay? Okay, let me go one more, and then we switch subject. Okay?
Sorry?
Yes.
Can you explain briefly again the meaning of arrows coming in or arrows
Yes.
going out? Like
It's a good point,
what
yes.
meaning is?
So maybe yeah, it's a good place where to explain it. Take the Pauli matrices. When you think of them as Pauli matrices, they are matrices. One index is up and one index is down. Okay? So up or down in diagrammatics, you can think of it as arrow going in or arrow going out, so that you can keep track of them. So when I write state, the state that is any state, you can choose first the basis that is the basis of the full Hilbert space, and then you say the coefficients on that basis, they happen to be such that this one is an invariant. Okay? And so these coefficients are supposed to have all the indices all down, because these are all cat states. They are not brass states. Okay? So this one is not directly a Pauli matrix. It's a Pauli matrix with one index lowered. How do I lower one index? What is time reversal? It's just epsilon alpha beta. Okay, so this one down is just Pauli matrix, an index down, with an epsilon alpha beta. Okay, let's go ahead. I just have to fill in, how do you do it with many? I think the logic is clear. You have many spins. You want to write a state that is invariant under rotations. You don't just want to write a state, you want to find a basis of the Hilbert space of objects invariant under rotations. one practical way of building this basis is, well, you first combine the first two, choose an ordering. You combine the first two, you find there is virtual spin. You combine one more, virtual spin. One more, virtual spin. This defines a tensor, just obtained by the contraction of all those 3J symbols. You put it here, you get a basis. Okay? What is this basis? It's the basis of simultaneous eigenstates of total spin being 0, so that you know that it's an intertwiner, and total spin of these two being K1, 1, 2, 3 being K3, 1, 2, 3, 4 being K4. Okay? And you can check, and you should check that all of these ones commute with each other so that they can be simultaneously diagonalized. Now, I'm going to skip an idea in this point and make a comment. If you go back to the picture of the tetrahedron that Carlo was describing, each one of these spins is a normal. If you have two normals and you take the sum of the two normals square, this measures the angle between the two normals. And so what one is doing here is to select a set of angles between faces and say, I can simultaneously diagonalize them. And this is a basis, so this thing that I was giving you up here, it is called the recoupling basis in combinational angular momentum, is geometrically the basis that diagonalizes dihedral angles, a set of them that commutes. Okay? So it's not a very democratic basis because you have to choose a sequence, and so diagonalize some, but not all of them, cannot diagonalize all of them. So what I want to do next is, let me describe another basis that is way more democratic, it's way cleaner as a way of thinking about it. But if you have to write a code or you have to do a calculation, it's way more difficult to work with. It often happens, no, that there's this trade-off between what is helpful as a computing method and what is helpful as a conceptual description. So there's another way of building a basis. After all, if you want an orthonormal basis, you just need an observable, and you look at eigenstates of that observable. So let me just consider on the Hilbert space of many spins, some Hamiltonian that happens to be non-degenerate. So if the Hamiltonian has a non-degenerate spectrum, the basis of eigenstates, the eigenstates provide a basis of the Hilbert space. Now, how do I build an Hamiltonian that is non-degenerate? Well, something like a random matrix would give you that automatically. Something sufficiently complicated would give you that. I also want an Hamiltonian that commutes with global rotations so that it has a sector that is total spin 0. Okay? So for instance, you could think of, if you're familiar with many body spin systems, the random Heisenberg Hamiltonian is exactly of this kind. And you would just take the sector of spin 0, the random Heisenberg Hamiltonian. And that would give you a basis of intertwined spaces. So if you are interested in contributing in that sector in condensed matter theory, these methods can be helpful. There is something very similar that is what Carlo described when he was describing these states here. Nodes labeled by oriented volume over node. You can think of that as an Hamiltonian that is invariant under rotation. It's actually the volume of a polyhedron. Okay? And it selects the volume, but then it doesn't commute with the other quantities. Okay, and this was jumping ahead. I just connected quickly some of these mathematics to something I'm going to describe later. Comments? Even going back to the previous examples if you want. Yeah.
Yeah, so could you mention again what it means, this sum where you have this small, so you have a sum of j's from 1 to n with small n. It's not in this slide, it's a little bit later on, I think.
Tell me where?
Here.
This one.
Yeah, this one. Could you comment on that?
Yeah. This point here, right?
Yes, yes, please.
Yeah. So I'm saying making two statements. This state is invariant under rotations. That's the first statement. How do you check? Well, you have to check that if you rotate, if you have to have a SU2 transformation on this state, that transforms each one of these vectors with a Wigner matrix. So that Wigner matrix, you can move it on this tensor and ask if this tensor contracted with n Wigner matrices on each one of the indices is invariant. The tensor, I'm describing it pictorially with this graph, and so you would have a Wigner matrix attached to each one of these ones, and by the fact that this has this structure, it should tell you that this is an invariant tensor and it doesn't change when I transform it. So that was the first statement. This is I'm repeating the statement, this is an intertwiner. But then I'm arguing more. This is not one intertwiner. If I vary k, I'm spanning over an orthonormal basis of intertwiners. And if I count them, I also know the dimension of intertwiner space. Okay, so I gave you k, but now I want more. I want to know the interpretation. Having a basis with a label gives you the basis, but you also want to know labels of what. Okay? And so this is the answer to that question. If you compute the operator that measures the square of the sum of these two spins, this state diagonalizes that operator with the eigenvalue k times k plus 1. And it does it for all this set of observables. Okay? And just to be clear, all this is very technical, takes time to absorb, but they are tools that then are useful, and it's good to know which ones are the things to pick up first to build the rest. Yes?
But k isn't fixed, no? K is all possible values.
If you span through all possible allowed values, you span over all of the elements of our orthonormal basis.
And then Kn is, are we also summing over all possible values for K?
Think in the same way as you think about eigenstates of the Hamiltonian or the hydrogen atom. You can take an eigenstate, you have to give n, j, and m, and then any other state can be written on that basis. So yeah, what I'm giving you is just the labels for each one of the states in this basis. Okay? In that sense, they are not summed over because this is just one state. Okay? Yes?
So what is this kappa n? Because in this last equality, we know that cats are enumerated by kappa 1, kappa up to n minus 2, and we have kappa n on the right-hand side.
Okay, small n. You're referring to this, right?
Yes.
Yes. Okay, so you're asking what is this small n?
What is kappa n?
Oh, okay.
So is it just with type?
Okay, so let me say it again. So this small n goes from 1 to n minus 2. So you could choose. You could take this n equal 2 and say, what is j1 plus j2 squared over all of this? It gives you kappa 1 times kappa 1 plus 1. Okay? Good. Yes, go ahead.
It's basically a follow-up question. So why can you only do J1 plus up to Jn? So why can't you do like J3 plus J4?
Good. You could, and that's another basis. Okay? And between these two bases, there's a unitary transformation sense one to the other, because they are two orthonormal bases.
But this is the one that has the interpretation of the hedral angle.
This one has the interpretation of the hedral angle between this set of the hedral angles, 1, 2.
There's an n plus 1.
Okay,
What formula did you want? n minus 1, I suppose, with the little k, and that's what people are getting confused. Try for n equal 3. Or try to the j little n equal 2. The eigenvalues is little k 2 1 not 2. With respect to the picture, or label different the picture.
Let me address first.
Sorry.
Let me address first the question. So you're saying, yeah, I chose one ordering. I could have chosen another ordering. I would have another basis that diagonalizes another set of compatible observables. Now these two sets of observables that don't commute. Let's do it just for 4. So I can do 1, 2, 3, 4. So this is like saying, suppose that I measure the angle between these two, then this one is an eigenstate of that operator. But then I could also do something else. I could do another channel where I do 1 with 4, diagonalize this one. Okay? So this is an eigenstate of one observable. This is an eigenstate of another observable. This one, if you span over k, you get a basis. Here you get a basis. But they are not the same basis because the observables don't commute. And Carlo was asking about n. So let's suppose that n is 4. Yeah, I should get n minus 3 maybe.
Let's try k1, little k1. Little k1, the red one,
yeah,
is j1 plus j2.
Yes.
So j1 plus j2,
yeah,
n equal 2, that's 1.
I see what, yeah. Okay, absolutely. I count that, yeah.
Little n minus 1.
On the left you want it.
Or plus 1 there.
Yeah,
no,
good.
plus 1. Plus 1 there or minus 1? Plus 1 there is
yes. I agree. You're absolutely right. Thank you. Okay. Let's go ahead. Tell me it's okay. We shift subject. We start again. Polyhedron. Yes. Yes.
Regarding the very last point you made,
yes.
Random Heisenberg.
Yes.
So why does it eigenstates corresponding to this oriented volumes? Is it easy to understand?
No, I'm not making the claim that random Heisenberg and oriented volume they are the same. I'm saying they are. One gives a basis, volume gives a basis. Okay. Random Heisenberg is well studied. Volume for n equal 4 is well studied. For higher n is very difficult. It's way more difficult than random Heisenberg. No, random Heisenberg is quadratic. This one is not even quadratic. I saw there was an end up. Was there an end? No. Okay. Good. So it's a similar class of problems. That's what I was hinting at. Okay, let's start again now. So I do classical geometry. I do polyhedra. The message is, if you take this thing, you quantize it, you get what I was describing before. So I have to tell you first about the classical thing. Okay? And I could do first tetrahedron and then polyhedron, but Carlo has done that. So I'm going to rely on what he described for the tetrahedron and on the fact that we already discussed it earlier, and I'm going to take a case that's slightly more general, and sometimes it's helpful to be slightly more general because you avoid the degeneracy of things that are confusing because they happen to be the same. So let's start in this way. Let's take a polyhedron. As usual, I should declare what is fixed, what can change. The background structure, what is fixed, is that I'm speaking about three-dimensional Euclidean space. Okay? So the only thing that I can change is the shape of the polyhedron. I'm not speaking about the metric. I should say what is a polyhedron. So there are various ways that are equivalent at this point, and then at some point I'm going to want to make a jump and introduce a phase space that is making it into a classical system. Before I go there, let me list these things. So a polyhedron, you can think of it equivalently as and I should say a convex polyhedron. I'm interested in a convex polyhedron as a convex hull of something. You can think of it as a convex hull of a set of points. You take all these points, you take the convex envelope up to rotations and translations. So this is a description of the kind, give me the position of the vertices, and then if you ask how many degrees of freedom there are, well, it's not immediate to count how many degrees of freedom there are, because suppose that one of these vertices, I move it and it goes inside, then it disappears, because the convex hull doesn't count it. So this description is not so helpful for counting degrees of freedom, and it's, as I was giving already the message, the description really helps is go to areas, okay? I'm gonna make one more comment before I go ahead. You know that there's this Euler theorem that tells you how many faces something has in terms of how many edges and how many vertices. And so the description in terms of vertices takes this one as fundamental. Often one works with edge lengths. You take edges as fundamental. What I'm taking is faces. The number of faces is what I'm fixing. Keep that in mind, because number of faces is fixed, and when I move things, the number of edges and vertices are going to change. This doesn't happen for the tetrahedron. No? Okay, so how do I do it with vectors? I'm saying fix the number of faces. N is fixed. What I need to know is what's the size of that area and what's the direction. And then, well, there is a fact. If you start with a polyhedron, there is one arrow that is always easy. If you start with one polyhedron, let's say this one, given its shape, you can compute this normal, you can compute this normal, you can compute each one of them, and you can check that the normals sum to 0. It's a fact, if you want. It's a Gauss theorem, or the fact that it's not moving, as Carl was describing, means that the sum of the pressures is 0. That means that this is 0. The question is it true also the reverse? That is, if I give the areas, I determine the polyhedron uniquely. And how uniquely? So that's where I'm going. And this is actually a classic result. It's Minkowski's theorem. The theorem goes this way. I described one arrow. Take the polyhedron, compute the normals, and then take this set of normals, think of them as, I don't know, porcupine, something that has just vectors all at the same point. You can check that these vectors sum to 0. That's what I was saying before. This is easy. Given a convex polyhedron, we can compute area vectors, and they sum to 0. The difficult part, which requires a theorem, is the reverse arrow. Suppose that you are given a set of vectors, which I'm going to call areas, but this is just a set of vectors, that happens to sum to 0. Is it true that there always exists a polyhedron that has that set of vectors as normal? And is it unique? And the theorem answers, polyhedron exists, and it's unique up to rotations and translations. Okay? And the polyhedron is the polyhedron with areas that are the norms of the vectors and unit normal given by the direction. I should say that the theorem is only a theorem, but not a constructive proof. And actually, together with Pietro and Simone, we worked through that. We learned how it works. Like this paper contains lots of the details, and if you want a picture that captures something of the algorithm, how would you construct this? You can think of it this way. You start from this one, take the plane that is normal, and start moving it in this direction. Then you take this one, you start moving it in this direction, as you see here. And then you adjust by how much you move them until the intersection is the correct area. And so this is a constructive way of building the polyhedron out of the normals. Okay? You just think of this as a small bubble, and you inflate it, and you get this one. Okay? I'm gonna go through a list of remarks and then I'll let you ask questions on this part. So first, adjacency. You see, you have a list of, you have fixed the number of faces, let's say 6. Now, if I take this set of vectors, it turns out to be a cube or a cuboid. If I move these vectors a bit, I can easily change the number of edges. I could get something that is here a triangle, there a triangle. If I move it a bit more, I can get something like a pyramid, basis that is pentagonal plus 5. And you can check with Euler theorem that when you put all of them together, it still works. It's a theorem. No? Now, all this gives you shapes, but it doesn't give you yet a dynamical system. Is there a comment? Let's go ahead. So now I'm going to make it into a dynamical system. To make it into a dynamical system, I need a phase space. I'm not going to derive phase space out of some Lagrangian and doing canonical analysis. I'm going to postulate it. I'm going to say these are vectors of fixed area, so they are points on a sphere, and there's a unique rotational invariant structure on a sphere. And so I'm going to just take the unique object that has the correct transformation properties. And so we did it for the area vector. We know the structure. It's unique up to rotation. If I have n of them, I just have a Cartesian product of many phase spaces. But now I have to impose a constraint, the constraint that all these vectors close. There is more. I was saying it's constructed also up to rotations. It's the same polyhedron up to rotations. Now, once you build this phase space and you look at this object, there are non-trivial Poisson brackets between areas. So when you take this constraint that the sum of the areas is 0, this Gauss constraint, and you look at the transformations that it generates via Poisson brackets, it turns out it actually generates rotations. And so if you ask that it closes and it's invariant under rotations, what you're actually doing, that's this statement, yeah? It's the generator of rotations. What actually happens is that you have what is called a symplectic quotient or a symplectic reduction. That is, you start from your initial phase space, you impose the constraint that the sum of the areas is 0, and you mod by rotations, and that gives you the phase space of a polyhedron. Okay? And you can check that, let's say, if you do 4 phases, you get that at fixed areas, there's only 2 degrees of freedom left. To say what is the shape of a tetrahedron, one could say you need 6 edge lengths, or you can have 4 faces and you need still 2 things to describe completely its shape. And you can think of it as, well, you tell me how it's opened up at one edge, and how I twist opposite edges. Or you could say, I look at what's the volume and what's the circumradius. Now, the volume doesn't tell you the shape, but it gives you a scale. And then you can ask, what is the smallest sphere I could pack it in? It tells you how elongated it is.
Sorry?
Yes?
Can you explain again what this symplectic reduction is?
Yes. Yeah. I can repeat exactly what I said, but this is a way bigger topic. And it's the topic of how, when you start from a system in phase space that is unconstrained, what happens when you impose constraints on the variables and mod by transformations generated by those constraints. Okay? So maybe something that helps is this. Phase space is always even dimensional. No, for instance, for one particle in one dimension is 2-dimensional, QMP. in 3 dimensions, Q and P 3 times. Now I put a constraint. Suppose I put only one constraint. For instance, I fix the energy. I would do 6 minus 1, 5. This is not a phase space anymore. How do I get a phase space? I have to subtract always something even. Okay? If you fix the energy and you mod by time evolution, you're cutting away 2 things. You're taking away the energy shell and the position on the energy shell. Okay? That's the simplest example of a symplectic reduction. And here you are saying the sum of the vectors is 0, and that sum of vectors generates a time evolution, an evolution that just rotates things. And to appreciate why a constraint also generates transformations, so that is something worth taking the time to go through it. Okay? There's a quantum version of all these things. That is your quantum constraint, the Gauss constraint in electrodynamics, that constrains your dynamical variables, but also generates gauge transformations. The names happen to be the same for a good reason once one goes to all the analysis. Okay, so I think I can skip the origami and only tell you one thing, that is, once you go through this construction, you have a phase space, so you have Q's and P's, and you can say, just quantize it, as we know how to quantize anything once you have the classical theory. You quantize a classical polyhedron, what are you going to get? You need a name, quantum polyhedron, right? You know what is it, because you know what is the classical object. Now there's a doubt that one could have, that is, wait, but you started with something that was unconstrained. You first constrained it, and then you quantized. What happens if I first quantize it, and then I constrain it? Do I get the same thing? And there are always these subtle things when one looks at systems that are non-trivial. Those quantization commute with reduction. Here there's a theorem, Guglielmin-Steinberger theorem, that assures you that everything is under control in these cases where there's sufficient structure. Okay? Okay. Plan for the last part is, let's connect the two. Classical polyhedron and all the story of these invariant tensors. Before I go there, yes?
Just a question. So, in this theorem, how is quantization defined? Because when we first quantize and reduce after that, how we... Because when we first do constraint and after that quantize, I can imagine what that means, but what it means to do reduction on the already quantized system.
Yeah. Okay, so let me address that. You could take all these vectors, you know how to quantize each one of the vectors, they just spin. And then the constraint is just a condition, the sum of the spins has to be 0.
On the state of the Hilbert space.
Or the Hilbert space.
Okay.
Okay? So this is, you first quantize and then you impose the constraint in the quantum theory. Or you could do the other way around. You can say, I had the classical system, it's many vectors. I first impose that these vectors sum to 0 up to rotations, and then I quantize just the Q's and the P's without any redundance. It's more difficult to quantize something that is constrained, but it's also just ordinary quantizing Q and P's, and the two things happen to coincide. Why they coincide? Because quantization is not that it's a process, a rule. It's not. There are. What is always under control is you take a quantum theory and you can look at the semi-classical limit, but there are many classical theories that correspond to the same quantum theory. What makes it rigid here is that there's lots of symmetries, and so you ask for the quantum theory that has the exact realization of those symmetries.
So what are assumptions of this theorem? They are like quite general, or?
They are quite general, but they definitely bring in the fact that you have a phase space and you have the action of a group on that phase space. And the quantization is a quantum theory that has representations of that same group. And so you're not breaking the symmetries. That's what fixes the ambiguities. Okay, let's go ahead. Quantum polyhedron. So first line is what is on the blackboard here. You take n spins. This is unconstrained n spins. Then you impose the constraint. The constraint is that the sum of the spins is 0, and therefore this object is invariant under rotations. Okay? And you can write it as a state that belongs to this Hilbert space that is written on this basis of many spins with this tensor. Then now I'm not going to write it anymore as a tensor because we learned you can describe a tensor. A matrix is a line with two indices. A tensor with three indices is a dot with three legs. And if you have something with n legs, it's a tensor between all of these representations. Okay? And you could take this recoupling basis that I described, or other basis, but now we have more. We have an interpretation. We have the interpretation that each one of the spins is essentially an area vector, that the constraint that tells you that the sum of these vectors is 0 is actually the constraint that this object is invariant under rotations. It is an intertwiner. Now let me go one step beyond. That is, let's look at observables. When you think of the polyhedron, you can ask questions of the kind, look at phase 1, in what direction does it point? But those questions would require that you have an external reference of what is direction. So if you ask only intrinsic questions, only questions that are invariant under rotations, there are always questions that ask, what's the angle between this vector and this vector? What's the triple product of these three vectors? What is the volume? What is the shape, but not the orientation? They're all questions that are invariant under rotations, that in the quantum theory means the observables commute with the constraint that generates rotations. You can think of it as this one generates transformations of O, and that transformation is trivial. Okay? And now clearly, as states are annihilated by this constraint because they are invariant under rotations, when you act with these observables, because they commute with the generator, these observables send states into states. So area is good. It's invariant under rotations. Angle between phases is good. Volume is good. And there's a full list of observables that one can look at. So now maybe I can go back to the quantum tetrahedron and just say it again. If you look just at the area vector 1, that's not invariant under rotation. So it's not an observable. The modulus square is an observable. It's the area. If you want an observable, you can take the scalar product of 2. So you take one direction, another direction, scalar product. That should tell you the cosine of the angle between the two. Can you find what are the eigenvalues of the angle operator? Suppose that you were to measure the angle between two faces. What are the possible outcomes of that measurement? Well, here just if J1 plus J2 squared gives you k times k plus 1, then out of that you can get the scalar product and you get the spectrum. Okay, so that means that this state is an eigenstate of the operator that measures this angle. Now, before we were wondering about different recoupling channels. So this one is an eigenstate of this angle between these ones. This one is an eigenstate between angles between these ones. But these two observables don't commute. The observable that measures the angle 1, 2 and the one that measures the angle 1, 3 don't commute because A1 with A1 have a non-trivial commutation relation. You do this calculation, A1 with A1 gives you epsilon A1. Now you have a triple product. You look at this and you recognize it. This is what Carlo was describing when you do the volume. You can write the volume as the triple product of three normals. No? If the normals align, the volume is 0. So they have to span something three-dimensional. So you learn that the commutator of two angles gives you something proportional to the volume. Let's check dimensions. Area squared, dimension 4. So am I doing it right? Yeah. So this is 4, 8. This is 6. So here there's something, 6. and then there's an area. Good. Or if you want area, 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 area. Good. So if this is the commutational relation, then it means that if you take a tetrahedron and you find that this is not an eigenstate of area of angle 1, 2, but it has some dispersion in 1, 2, then there are Heisenberg uncertainty relations for 1, 2, 1, 3. This product, it's like delta Q, delta P has to be larger than h bar over 2. Here it's delta angle 1, 2, delta angle 1, 3, larger than volume squared. It's Heisenberg uncertainty relations for quantum geometry. Comments? Yes?
Is there any reason why this volume squared has a factor of 2 over 9, and then in the uncertainty relation you have a factor of 9 over 2 again?
So the volume happens to be 2 over 9 when you check the volume of a tetrahedron. Here you get area, 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 which is 2 over 9 volume squared. There's
so
nothing more.
This factor 9 over 2 appears there again, is just a nice coincidence.
Oh no, it's not a coincidence. It's you know that if you have these commutation relations, then there's Heisenberg uncertainty relations with here the expectation value of the commutator. Yeah. Okay, so this thing is the expectation value of 1, 2, 3. The expectation value of 1, 2, 3 is the expectation value of 9 over 2 v squared.
Yeah.
So there's nothing more than that.
Yeah.
Okay? Okay, and this 1/2 is the usual 1/2. More comments? So these are quantum polyhedra, and before I was describing things that were classical, and I'm saying if you take the classical thing and you quantize it, you get the quantum thing. Can we go back? You start with the quantum thing, in what regime do you get back the classical thing? So let's do it first for one spin. If you have one spin, I was thinking of one spin as you take a direction, you quantize it, and you get as one spin. But then, is it true that Jm is like a direction? Well, J plus J, you would say, points up. J minus J points down. But Jm, J0, it's not that it points there, right? It's this complicated spherical harmonic. So how do I make something that points in that direction? One thing that you could say is, well, don't diagonalize Jz, diagonalize J that direction. Another thing you could do is think of it as a coherent state where you peak over some direction. It turns out that every time you have a system, you can look for semi-classical states that have a given expectation value and a small dispersion. But when you have a group theoretical structure, there's way more that you can do. You can use that group theoretical structure. So for spin systems, you could say, let's try to pick on a direction. Let's say you fix the area, and then you ask, can I write a state that points in the direction of that I fix, direction n, so that it points in that direction and the dispersion is small. But there's a nice geometrical way of doing that. That is, you just first point up, and then you rotate with the rotation matrix. This is a completely general structure you can do every time you have a group structure. Those are called parallel of coherent states. And it's summarized here. You start from J plus J, and you rotate down. There was a comment. Was there a comment? No. Okay? So you can do it for one vector easily. But now you know that the polyhedron, you can think of it as many vectors with the constraint that they sum to 0. And the amazing result that entered even before the polyhedra were clear is this Levin speciale coherent states for the tetrahedron and then for the polyhedron that are take first vectors in some directions so that the vectors sum to 0 and they give you a polyhedron. Now, this tensor product of these states. This is not invariant under rotations yet. It's only invariant in average. But you can project over invariant by doing the group averaging. That is, you rotate all of them and you integrate over rotations. And that gives you an object that is labeled by the normals and is an intertwiner now. Okay? Or you can obtain it in some more sophisticated way by identifying directly the structure that is invariant under rotations. So now I have a picture that is, if at the classical level you have a phase space, let's say n equals 6, and in this phase space n equals 6, there's somewhere in phase space there's something that corresponds to a cube, somewhere in phase space something that corresponds to this wedge, somewhere else in phase space. Actually, we mapped the phase space, the 6-dimensional one, and there's, like, if you look at 1, 2, there's when 1 and 2 touch classically in phase space, and 1 and 2 can be opposite phases. Okay? They all belong to the same phase space. So as you move through phase space, classically, you can deform this cube into this cube. In fact, you can see it. No? You have 1, 2. It pinches at one point, and they become two triangles. You have this edge that elongates, and then this base that shrinks. And you send one cube into the other smoothly, going from here to here. And now think about the quantum theory. In the quantum theory, you have states. And now I'm asking, can you write a state for a cube? First of all, which cube? Let's say this one. So the one that corresponds to this point. Okay? But the state is a coherent state, so it has as average this cube, but it has fluctuations around the cube. You can think of it as a Gaussian peaked around here. But this Gaussian has also tails, so the fluctuations around that average, they are cuboids, and there can also be a tail that enters this other region when it's not even a cube. In fact, you can be even more drastic and do superpositions. You could say, suppose that I take a coherent state picked on this cube and a coherent state picked on this pentagonal wedge. Can I prepare a state that is the superposition of the two? And from Sugado, we heard how one can prepare in the laboratory, how one can build superpositions of geometries by superposing masses in different places. In superposing masses in different places, you are superposing geometries, different geometries. Now, perturbatively, there's a lot that one can do, but non-perturbatively, there's always the question of, do you have full control of the set of states of the geometries and of semi-classical geometries? And this is a very simple system where I'm not speaking about gravity unless you think of it as a node of a network. But in this very simple system, you have geometry, quantum polyhedra, and you see that if you take an eigenstate of the volume, one of these states where the volume is defined, that state is something like a line here that corresponds to a superposition of all those shapes. If you take an eigenstate of the angle between two faces, this is some other line in here that corresponds to some other superposition with very specific coefficients. If you think of a coherent state, then coherent state you can pick it here, you can prepare one, then you can think of a protocol that makes it evolve into a superposition of this with that. I don't know how to build a Stern-Gerlach for polyhedra, but that's the picture, okay? And in spin forms, the elementary transitions are you start from a node of space, and its node of space can split into a number of nodes. And you can ask what's the transition amplitude from going from one shape or one node, one polyhedron to, for instance, 4 polyhedra with fixed shape. But don't forget that this is an S matrix element. This is like I'm fixing the in state and the out state. But if you ask the other question of, suppose that I prepare this state and I ask how it evolves in a superposition of things, in a superposition of all of these things. So dynamics does it for you. And I think this is a good point where to pause and let you ask questions. Comments? Yes?
So if you take, say, a random, an eigenstate of the random Heisenberg,
Yes.
right? Then by taking the overlap with these coherent states, you should be able to get that kind of picture,
Yes,
right?
absolutely. Absolutely. Yeah, so, okay, so I think I should expand on this point because with Pietro and friends, we have been thinking a lot about random Heisenberg, and one doesn't have to think of it necessarily as a condensed matter system, one can translate it here. So let me repeat it briefly. Suppose that you have 6 spin 1 half, and you take an Hamiltonian that is scalar product of 1, 2, 1, 3, and all possible couples. The Hamiltonian is sum over all possible coupling of 2 with random coefficients. Okay? Now this Hamiltonian is invariant under rotations because they are all scalar products. So you can ask, what are the properties of the ground state of this Hamiltonian? It should be a state invariant under rotations. In fact, that's not the unique state under rotations. There are going to be many states under rotations. Well, each one of these states is an intertwiner state. Okay? And so you can think of it as a quantum polyhedron. And so now you can ask what kind of superposition of classical polyhedra it is, or does this polyhedron as a coherent state have an interpretation in that condensed matter system? All of these questions are formal questions, but also questions that can help in some of the things that one addresses there in that setting. For instance, one can ask, you can think of it as a chain of spins, all coupled first neighbors. Then you take the ground state and you ask, how entangled are these spins with those spins? But that's a question that here corresponds to asking, how entangled are the angle between these two faces and the angle between these two faces? Okay, comments? Yes.
I want to ask about the phase space. What properties of polyhedron are the P and what are the Q?
Good. I go back and do the thing that I skipped.
Oh, I missed it.
No, I skipped it because I wouldn't need it, but now.
Okay.
So let me describe this thing because I think it just says what is Q and what is P. I just skipped on what is Q and what is P. You have all these vectors, and they have this complicated phase space where vector with vector Poisson bracket gives you another vector. But we like Q with P Poisson bracket gives you 1. So can you find Q with P Poisson bracket gives you 1? Is there a canonical transformation sends you into familiar canonical variables? And these two mathematicians found not the map from here to here because they didn't know about the polyhedron, but they were interested in a similar problem. So take these vectors, order them, and now first vector you attach the second vector, and the fact that the vectors sum to 0 means that this one is a polygon. But it's a polygon in R3, so think of it as an origami, something that you draw and then you fold. So there's a fold here, another fold here, another fold here. So what is P? P is the angle between 1 and 2. The angle between 1 and 2, you can measure it by looking at how long is this crease into the origami, this fold. Okay? So this P is exactly this recoupling spin in the quantum theory. Okay? And what is Q? Well, once you fold here, you have to tell me how much you have to fold. The angle. And so this angle of the folding, you can check and compute and show that Q and P are conjugated, and this Q and P are decoupled from this Q and P. Okay? Q is an angle.
Okay.
When you quantize something that is compactified as an angle, you get the conjugate momentum as a discrete spectrum. Okay. Angle operator has a discrete spectrum exactly because of that.
Okay.
Okay? So having control of the classical theory doesn't give you just interpretation. It gives you all the intuition that comes from the fact that once you understand the classical theory, you know also lots of property of the quantum theory via Bohr-Sommerfeld and correspondence principle.
Okay.
Yes?
Just to clarify, so like coherent state and semi-classical geometry, are they synonymous to each other? Are they the same?
Good point. The relation between the two is that semi-classical is a broader, less precise notion. Semi-classical just means there's an average that I interpret it as the classical value, but there's also always some dispersion around that average. So it's not fully classical because it's fuzzy. Coherent, people use it in a way more precise way by saying it's one specific mathematical under control definition of semi-classical. For instance, if you have a free particle on a line, everything peaked and sufficiently narrow is semi-classical, but the Gaussian, you call it coherent. It's exactly the one that you prepare it Gaussian, and with a free particle evolves as Gaussian, and has all the nice properties under some transformation group. And so these ones are coherent in the sense of this transformation group. There's another notion that always comes together with coherent that is squeezed. You can prepare it coherent, and then you change some of the dispersions, and so you make one coherent and then you squeeze it out. What's up? Yes?
So what is the geometrical interpretation of PNQs? Is there any?
Yes. So let's go to the tetrahedron. So tetrahedron is 4 vectors. And I was saying, I'm thinking this as the porcupine, and then I order them and I get this origami. So in the origami, P is the sum of 1 and 2 squared. So it's the sum of 1 and 2 squared. So P is the angle. Okay? Because the sum of 1 and 2 essentially measures. Huh? I'm not saying it's the angle, is related to the cosine of the angle. No? So what is the conjugate momentum? Well, it turns out that it's you can draw a tetrahedron by drawing first one edge and then the opposite edge, and then you connect the vertices. Okay? So can you see the tetrahedron? This is a tetrahedron with this edge, and then you have to add all the other lines. Okay, so this is a tetrahedron. This is also a tetrahedron. Okay, so what is Q? Q is the angle between this one and this one. So you can fix the 4 areas, and then what you're left with is a 2-dimensional phase space where you change these 2 variables and they don't change the area. You change the angle between these 2, you can change it without changing the other angle.
Yes.
Or you can fix this one and twist it. So dihedral and twist angle. Those are essentially Q and P. Okay?
And both are quantized.
Both are... Attenzione.
Discrete spectrum.
Attenzione. Both are variables in the classical phase space, and now I can ask, is there an observable in the quantum theory? And the answer is yes. So you just put hats and you get observables in the quantum theory. Now, both are quantized. That's where I'm saying, let's be careful. It's not a statement that a quantum tetrahedron has discrete values for these quantities. These are observables, so you can ask, suppose that I make a measurement of this one, I find only one of the eigenvalues of that one as outcomes. But all of these observables, they don't commute with each other. So every time you write a state, it can be an eigenstate of some of these, but it's not an eigenstate of all of them. That's all the warning that I have. No? They are all quantized in the sense that they are all observables, all operators. If you're asking, do they all have a discrete spectrum? Well, the Hilbert space is finite dimensional. So these are all matrices. No? But they are matrices that don't commute. And a good exercise is write explicitly the matrix. Do 4 spin 1/2. So 4 spin 1/2, I said you get only 2 possibilities, so they are all 2 by 2 matrices, and you can diagonalize them pen and paper 2 by 2 matrices. But you can also show that the angle between this and this is a matrix, the angle between this and this is another matrix, and they don't commute, and there's another matrix that gives you the volume. Okay? One more comment?
So, if I have a node and 4 of these lines coming out of it, that's a tetrahedron, right? And then let's just do the simplest one. I have 1/2, 1/2, 1/2, 1/2, right? And then you do the recoupling basis. Then you have essentially 2. Actually, you have 1/2, 1/2, 0, 1/2, 1/2, and then 1/2, 1/2, 1, 1/2, 1/2. I guess the first question would be, physically, what does a 3-valent
good. Yes.
refer to? And then physically, what does the one in the middle when you have the recoupling?
Good.
What
Good.
physical?
Yeah, let me address that quickly. Let's start with 6. Let's start with 6 faces. Suppose that one of the faces has 0 area, then you just pinch out that face and you get something like a pyramid. Then you can pinch out another face by setting 2 to 0, and you go from a cube to something with 5 faces to something like a tetrahedron. And now you're saying, let's set one more to 0. What happens if I take a tetrahedron and I send one area to 0? You squish down to something that's 2-dimensional, so the volume is going to be 0. So all the 3-valent ones like this one have 0 volume but non-zero area. So they are very degenerate. You can think of them as weird needles or pancakes. Okay? And then you were asking, what is this one? This intermediate one? Well, it's just you can have an angle that is 0, an angle that is something. Virtual one. Okay, let's close here. We can continue the discussion, and we can continue the discussion next time. I'm going to reserve time. We should be on 12:30 sharp for lunch. Thank you very much.